Today's presentation, Periodic Properties 2, is going to examine the properties of electron affinity, electronegativity, and also something called metallic character. Starting with electron affinity is the energy change that occurs whenever an electron is acquired by a neutral atom. Whenever an electron is picked up by an atom, there's always going to be either an energy gain or an energy loss from the atom system. And the electron affinity is the term that we give for that specific energy. When atoms acquire electrons, they're going through a process of reduction. Reduction means to gain electrons. Two possibilities from an energy viewpoint when a reduction occurs. One of those is that an atom, A, is going to acquire an electron, so atom plus E minus for electron yields an anion. It's got a negative charge plus some energy. This energy could be given off as light or heat most often. This is concerned especially if we're talking about heat. That's the main thing we're looking at here. If heat's given off, we call that an exothermic process, which means heat's released to the surroundings. And from the viewpoint of the atom, that means it's got a negative value because the atom has lost energy in this process as energy is given off to the surroundings. The other possibility is that we have a neutral atom with an added electron, and energy is being pumped into the system, and that yields an anion. So again, we have an anion. But notice here that energy is on the left side of the arrow here, the left side of the equation, and that means that energy has been put into the system. So we end up with A minus has more energy than A had to begin with. So in this situation, heat is going to be absorbed from the surroundings. We call this endothermic, and in this case we have a positive number of kilojoules per mole of atoms or per mole of electrons, whichever way you'd like to look at it, meaning that the anion that forms after the electron has been added has more energy, so it's positive. Now, in general, in nature, most things tend to proceed spontaneously from high energy to low energy, such as an object rolling down a hill. Objects don't spontaneously roll uphill. They have to be forced uphill by someone pushing it or work being done on it. So most processes in nature proceed spontaneously. That means they don't have to be forced from high energy to low energy. So because of that, this is going to have a tendency to favor exothermic processes. Exothermic processes, remember, release heat. So lower potential energy, the way that's done is by emitting heat. That makes it an exothermic reaction. Exothermic processes tend to be spontaneous. Notice that this is a tendency. Tend does not mean always. Processes that occur spontaneously are likely to happen, more likely than those that don't occur spontaneously. Therefore, negative electron affinities are more likely to occur in nature spontaneously. So the more negative the electron affinity, EA, the more likely the reaction is to occur, is one way to interpret that. Elements with more negative values for the electron affinity then are more likely to be reduced. And again, that is gain electron. Endothermic reactions have to be forced to gain electrons. These are non-spontaneous. Elements that are more positive in their electron affinities are likely to lose electrons rather than gain electrons. That is to say, they are likely to be oxidized. Oxidized means loss of electrons. So one way to look at electron affinity is it's a way to measure the attraction of an atom, a neutral atom, for electrons. The more negative the electron affinity, the more strongly attracted an atom is to its electrons. Now, the period trends first don't tend to be as predictable as other properties. And what we do is we look for the most positive and the most negative families. And those tend to occur in certain locations. The most negative values would be, for instance, here, here, and here. These guys at the most negative are the halogens, which is group 17. The most positive would be the noble gases, but also places like, which is group 18, but also places like group 2. The reason group 2 is very positive is because in group 2 we're trying to force a second electron into a half-full s sublevel, and that means we've got to push a negatively charged electron into a space that's already half full with a negative electron. So negative pushes away negative, so group 2 tends to have, it's very unlikely that it would actually gain one electron. We also have that halfway through the p block, so that would be group 15. Group 15 has a half-full p sublevel, therefore very unlikely to gain electrons, or less likely than you would expect with a very small atom. So group 15 tends to be more positive. Okay, so group trend, small atoms generally have stronger attraction for electrons. So we find small atoms at the top of the table. So we find more negative values toward the top of the table, and bottom tend to be larger, so less negative, moving towards 0. Not necessarily, they're not necessarily going positive, but they are going to be less negative than the ones at the top. So more negative electron affinities would be found at top of table. Okay. So as a general summary, and there's a lot of variation in this, so it's not quite as clear as this diagram makes it look, but in general, as we move from left to right across the table, we get more negative. As we move from bottom to top, we get more negative. But there are a lot of changes in this, somewhere like, for instance, this family, family number 2. Family number 2, very positive. This family, which is P3, so S2, the P3 family, which is family 15, 2, 3, 4, 5. D5 would also do a very similar thing, and if we have the Fs here, we would expect somewhere around F7 to have maybe a spike in the more positive values for electron affinity. Electronegativity, the second property in this particular PowerPoint, is a measure of the power of an atom in a chemical compound to attract electrons. The electrons that we're referring to are the valence electrons, those that we've already talked about with electron configuration. These are defined as the electrons available to be gained, lost, or shared by atoms when they form compounds with other atoms. They are of the outer energy level electrons, or as we've called before, the highest occupied energy level, electrons. Electronegativity is a calculated scale. It's not something that you measure. It's actually calculated based on some other properties. We will not get into the actual calculation. This concept was developed by one of our great American chemists, Linus Pauling, one of the few people who has been awarded 2 Nobel Prizes, one in chemistry and another as a Nobel Peace Prize. Anyway, he assigned fluorine, which is the smallest active element, an electronegativity of 4, and cesium and francium are given the lowest value, with cesium being the only one that's really worth mentioning because francium is very uncommon. Anyway, 0.7. So it goes from 0.7 to 4. Technically, it goes from 0 to 4 as an electronegativity. But nothing actually has an electronegativity of 0 because all atoms have some attraction for their electrons. It's just that cesium and francium are approaching 0, so not very much. So I said this is a scale. There are no units for the electronegativity in Pauling's calculation. And this is a very important concept in terms of chemical bonding. We actually use the electronegativity to classify the type of chemical bond that's formed between atoms. When we look at the trend, we can see one of the clearer trends. We have lithium to fluorine, an almost linear pattern, sodium to chlorine, potassium to krypton, rubidium to xenon. We have some D and F blocks here, elements here that tend to plateau things a bit, but regardless, we end up having basically from the left side of the table to the right side of the table, we have an increase in electronegativity. And increase electronegativity equals stronger attraction. So fluorine has a stronger attraction to valence electrons of other atoms than lithium does. Sodium has less attraction to valence electrons of other atoms than chlorine does. You'll notice that the elements like fluorine and chlorine are very highly electronegative, meaning that they have a tendency to not just be attracted to electrons, but even steal electrons away. When we look at the again, the period trend, you can see here going from hydrogen, helium's not listed. The reason helium's not listed is because it doesn't have an electronegativity, because it doesn't form compounds. In fact, the noble gases generally have a tendency not to be listed because of that. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. You can see a nice increase across as we look at the three-dimensional periodic table. Okay, you can also see from top to bottom the group trend. As we go down the halogens from fluorine to astatine at the bottom, there's a decrease in electronegativity. And you can see the same thing as we go from hydrogen down the periodic table to francium down here at the bottom. There's a gradual, actually a fairly steep decrease in electronegativities. So where do we find the highest electronegativities? Top right. Where do we find the lowest? Bottom left. Okay, our next property is metallic character. And let's look at some properties of metals. Metals tend to be lustrous, shiny, ductile. They can be stretched, malleable, meaning that they can be hammered out into flat sheets. They can tend to be good conductors of both heat and electricity. And most importantly, I would say in this section, is metals have a tendency to experience loss of electrons. especially when paired with a non-metal. So properties of metals, one big one that's often left out is that they tend to be losers. They lose their electrons, or they don't have very strong attractions for their electrons. So as we look at the general trend for metallic character, we find that we have the most metallic character down the table and to the left. So our elements over in this left corner are going to be those that have the most metallic character. They tend to, from an electron standpoint, they tend to be losers, strong losers of electrons, or in other words, they have very little control over their valence electrons. We tend to find in the upper right-hand corner, we would find our least metallic, whereas this side would be most metallic. Non-metallic character would be all the opposite properties. So I'm not going to spend much time on this, but we'll find that the most non-metallic elements are up here, whereas the least, which makes sense if you see metallic character, non-metallic character would be exactly the opposite. That finishes our presentation. Make sure that you submit your notes in a timely manner.